Hello, Chip Dippers. How are you? I'm doing okay. I was a little hoarse the other week, but now I'm much more stable. Anyway, about a year ago, I did a video of how to convert a Commodore 64 from NTSC to PAL. And there's a lot of reasons that you would want to do that, which I'll show you in a moment. But in the comments of that video, I got a lot of people asking, how come nobody's made a switch to do that automatically? Well, yep. Turns out there is a reason for that too, which I'll come to as well. I don't like to blow my own trumpet. But I've always been a bit of an inventor. And I don't just mean the Brick-64. Several years ago, I set up a company and a factory, and we made these products. And there's a tiny chance you might even recognize them if you were around in the 90s or the noughties. By the way, which did you prefer, the 90s or the noughties?
The what?
The noughties, like noughts and crosses.
Tic-tac-toe?
Okay, which did you prefer, the 90s or the tackies?
I don't know.
So I decided to put my thinking cap on, and I've teamed up with Sean Harrington, aka One Stage, Puppyfractic, and PCB Way! Yep, they are our very generous sponsor, and they've been supporting this project for the past year. It's kind of amazing, they not only get retro, but obviously all their boards can be used in computers from 30 years ago. The technology hasn't changed that much. This product is called the VIC-II², and now I invite you to sit back and join us as Marty, we take Vic to the future!
Welcome.
Now, before we start the exciting journey of actually creating this product, you're probably wondering, well, why is a switch so necessary anyway? So to understand that, let's take a brief history of PAL versus NTSC. Here's a photo I took of the Earth from the Moon. So NTSC became predominant in the 50s in North America and some parts of Asia. There was another format called CCAM, which we won't get into here, and then PAL was introduced 10 years later in the rest of the world. NTSC stood for National Television System Committee, but was less affectionately known as Never the Same Color. Oh yeah, and this was because it was notorious for not broadcasting consistent colors, and you may notice that only on US TVs do you see a tint knob. This was because it was really down to the end user at home to fix the color. Now watch closely as I switch to PAL on the same TV. You'll see that the height of those borders grow. Now, PAL stood for Phase Alternation Line, and it was created over a decade after NTSC, primarily to fix the issues with NTSC. That meant it had arguably better color accuracy, and there was no need for a tint knob on European TVs. Wait, where did my knob go? Well, on this occasion, size does matter. If we overlay the PAL and NTSC images, you can see that the PAL image has a higher resolution. And if we calculate out those aspect ratios, including the borders, you actually get over 20,000 extra pixels to play with in PAL. So what did this mean? What if we search the C64 scene database? We can see that in the American regions, there's 128 demos listed. That's cool, right? Until you see that in the other regions that supported PAL, there's over 3,400 demos. The other reason it is more popular there is due to the different frequencies PAL and NTSC run at. Per frame, there are more CPU cycles available to play with in PAL, and this combined with more resolution meant the demos could be more fun. Sorry, what is going on here? Oh. But it affects games too, of course, and actually the original reason I decided to convert from NTSC to PAL was because Ladyfractic bought me the Sam's Journey cartridge for Christmas a couple of years ago. I plugged it into my NTSC machine and, well, as I learned later here, the cartridge won't work on NTSC at all. But the other thing is composers like Rob Hubbard, they designed their music to sound like this. Not faster like this. Now, essentially, this was happening because of the difference in frequency of the American versus the European power supplies, and that meant that the NTSC machines were effectively clocked faster, with many people feeling that the games actually played better. And then finally, there's the age-old problem, which is, generally speaking, you can only use a PAL C64 with a PAL monitor and NTSC with NTSC. Otherwise, you'll get a stretched black and white picture. But that's not something we need to fix with a switch, because you can already use an upscaler, and that outputs everything in the global standard of HDMI. What we need to switch is what's going on inside the computer, not the display. So just to recap, PAL has these benefits, but, and it's a big but, no offense, NTSC also has a lot of benefits. Faster clock speed, you can use NTSC only programs, and also an important point, if you grew up in North America, the NTSC speed is going to feel more nostalgic and memorable, even if it wasn't how the composer intended it. So how do you get the best of both worlds? Well, the obvious answer is buy a PAL C64 for PAL software, and also buy a second NTSC C64 for NTSC software, but not exactly convenient, unless you could figure out some kind of switch that would allow one C64 to be, well, two. Thank you, Yoda. Now, if you've seen all of that, you might decide you just want to convert to PAL, and you don't need a switch. That's fine, you just follow the instructions in my NTSC to PAL conversion video, and Bob's your uncle, not Bob Ross. However, if we do want to be able to switch back and forth, there's essentially three components that we need to add a switch to. There's the VIC chip itself, which provides the graphics output. There's the timing crystal, which controls the frequency. And there's this jumper, which tells the motherboard and the rest of the computer to switch into PAL mode instead. And it turns out the reason nobody's done this before is because it's bloody complicated. So in steps Sean Harrington, aka One Stage, and he's one of my patrons, and reached out to ask if I had any projects that I needed help with. And so we put our heads together, and I invaded his space for almost a year. And the first thing that became apparent is there isn't a lot of space on this VIC area to mount the whole situation we'll need. So Sean sketched out this first prototype idea, and it basically uses this daughterboard design. A main, very flat, thin board sits on top of the VIC chip area, and then takes everything out through a ribbon cable where the hard work is done. And the theory is pretty simple. The daughterboard houses both a PAL VIC-II and an NTSC VIC-II, and the two different crystals. And then back on the backpack board is a switch and a connection to that PAL NTSC jumper that we saw earlier. And all of that should in theory allow us to switch these three items. You'll notice I'm saying in theory a lot, and that's because we have some doubts that due to the length of the ribbon cable, it may not be able to carry the signal from both VIC chips reliably. But we can test that theory, and this looks to be working. So the next thing we want to do is figure out the actual size of the product to make sure it will fit in the case. So for that, let's just 3D print some mock-ups of the two PCBs. This is the longer daughterboard. And it also popped out the main backpack board, shown here with a banana for scale. So come on, let's pop the backpack board on top of the VIC area and experiment with where the daughterboard could fit. Alright, so definitely some options there. So now there's only one thing for it. We've got to design the PCB, which as we all know stands for Perifractic's Cute Buddy. Yeah, Sean Harrington made Blockhead Perifractic for me too, because I'm a blockhead. Just kidding, this is actually me. Wait, what? Well, and Perifabric there is also holding a Commodore 64. It's almost as if he knew this video would happen a year later. And speaking of Sean, he's here with me now. Sean, can you just give us an illustration of how this PCB works?
So this is the backpack design. We've got 40 pins here that go into the VIC slot. We have 3 sets of optocouplers that do the switching between the NTSC version of it and the PAL. These are our logic chips that let us latch the power supply and the switch. Here are the 2 crystals. These replace the ones that are on the board. And this is the magic. This is a 50-pin ribbon connector that goes to the daughter card. This is how we have more real estate within this space.
That's right, and he mentions latching the power supply and the switch, and this is one of the biggest obstacles to overcome. Basically, we have to prevent the user flicking the switch while the machine is on, or it will fry both the VIC chips. Nobody likes fried chips. Well, almost nobody.
I think I'm gonna get the chips.
Chips? Oh, you mean French fries?
So you have to switch the power from the PAL to the NTSC circuit using the octocouplers or relays while the power is off. But how do you power relays with no power? And even worse, how do you prevent the relays working when there is power? It's quite a catch-22, or should I say a VIC-II². But speaking of catches, a relay will only latch when there is a power differential big enough to trigger the latch, in the C64's case, 5 volts. And we discovered that when the C64 power switch is off, that required differential does exist between these two poles. And it still gets power because the mains cable is still connected before the switch. But crucially, when you turn the machine on, that differential equals out. And so the relay gets frozen in place, it can't change positions with the power turned on, thus protecting your chips. So with that conundrum solved, let's look at how the daughter board works.
This actually has the NTSC and the PAL version of the VIC-II chip. We have 2 optocouplers here, which they don't switch all 40 of the pins, they only switch the main pins, the 5 volts in, the 12 volts in, the ground, and then the chip select. Here's the mounting point for the switch that switches between PAL and NTSC.
Thank you very much, Dawn of the Shed. Shaun of the... never mind. Yeah, well, anyway, the next step is to let the software calculate the ideal paths for all the traces. And then we send the Gerber files off to PCBWay! Because as we all know, PCB stands for Paths Correct? Brilliant! Now, when we're ready for mass production, hopefully at the end of this video, I'll take you on a full factory tour and show you how the PCB is made. But there's no time for that now because PCBWay, I'm not going to do that every time, PCBWay got these to us super fast to support this project. And they look great in a variety of colours. So let's crack on, put the first prototypes together and see if they work. And before long, we've got everything installed and the switch tested in theory, so let's try it on the Commodore 64. Fingers crossed. Isn't that the tune they play to the aliens in Close Encounters? Well, either way, this is, well, it's definitely an interesting effect, but probably not something you'd want to buy. And we think the most likely culprit is the length of the ribbon cable and some of the traces. You know, signal and noise interference is notorious for causing these kind of problems. So back to PCBWay, and they produced us another batch free of charge where we tried to reduce the length of some of the traces. And here's the result. Yeah, it still doesn't work. So the only thing left to do now really is remove the ribbon cable altogether. Now we'd created it that way primarily for using this product in the Commodore 64C, which has a much less space above the VIC chip area where it hits the keyboard. And it looks like there's no way to actually get this working with the C64C. Now don't get me wrong, we tried really hard. We even produced yet another batch with PCBWay, and in this one we tried to shift things a little higher up the board, but still it just wouldn't fit. We also switched the optocouplers out and replaced them with regular relays, and we did this for a couple of reasons. Mainly, they produce too much heat. However, we can at least support the bread bins, which I think it's fair to say are more common. Yeah, you're starting to see now why nobody else made this switch. Having said all that, if you are interested in a C64C version, fill out the little form in the description. Well, onwards and upwards, and let's move forward with what we are able to do, and maybe in a future revision we can start to accommodate the 64C. So it was back to the drawing board again, and we also engaged in some knowledge sharing with people on the Facebook group, including David Smith. Big thanks to him. Then off to PCBWay again, and we put Puppyfractic in charge of looking out for the delivery. which for some reason was happening in a swimming pool. And I've got the 8th version of the board here. Doesn't it look lovely? We're going to be selling this completely not for profit and only as a kit for a number of reasons, but mainly there just aren't enough hours in the day for me to mass produce these. But building the kit's a really great learning experience, although we can only recommend it if you do know what you're doing, which is a bit of an oxymoron, a bit like me. That said, do keep an eye on the official forum page, which you'll find in the description, because I'm sure people are going to come forward and offer to make these kits for you. So come on then, do you want to build this one with me? And then we'll test it out, see if it works, and if you eventually decide to buy this board, then this part of the video can serve as your installation guide. So obviously the first thing we have to do is remove the PCB from the case by removing these 6 screws. And here's some I removed earlier. Wait, where did I put them? Put that on eBay. And you may also have a shield underneath your board. I've already desoldered mine by removing these solder points. And then we just have to very carefully prise out our existing VIC chip. In this case, this Commodore 64 is set to PAL, so this is a 6569, but the 6567 is the NTSC version. You may also have a shield around the VIC chip area. Again, I already removed mine here by desoldering all of these solder points, and I did that in that previous episode. And then here's the timing crystal. This is essentially what makes the music sound too fast, but in this case this machine has a PAL crystal. So first thing we have to do is remove the crystal. And for this I'm going to use my trusty Hacko desoldering gun. This thing really makes desoldering a bit of a doddle, or if you're American, quite easy. As always, check out the description for the Get the Tools I Use link, and in there you can get the desoldering gun and any of the other items that you see in my videos. Next up, let's remove our jumper. If you're English, don't take your top off. Well, I mean, it's up to you really. And then I'm just going to make space on the board by flattening down these capacitors. Just bend them gently out of the way so they take up as little headroom as possible. And then here's our lovely board, and you can see that we've marked it very clearly so that you can only use the correct board with the correct type of motherboard. Right now we have 2 versions of the board which cover 3 types of motherboards, and I think what I'll do is just throw in both versions with every order so there can't be any confusion or mix-ups at the ordering point. Just make sure you check the assembly number on your motherboard itself, that it matches the VIC-II² that you install. So here's your kit, and just a quick disclaimer, some of these parts are going to change slightly by the time you get the product as we continue to perfect it. But the instructions will remain basically the same. Also, your board will only be red or blue. So first up, let's take this row of 40 machine pin headers. Cut them in half so we have a row of 20. And this is actually what's going to plug down into the original C64 VIC-II socket. So of course we've got to solder all those pins in place and make sure you insert the short pins into the board. Now you could use thermal tape. I'm going to try using mounting putty here just to hold them nice and straight. You might be wondering what that funky contraption is that's holding everything. Well, that is the helping hands. Again, check out the Get the Tools I Use in the description to get yours. And then we just get soldering. You've seen me do this before, right? Okay, nice. Just make sure you've got the long pins facing outwards and that those solder points have nice little peaks on them, kind of like tents. And then back to our male machine pins again. That means they have outies, not innies. And I'm just going to snap off 3 of those for the crystal area. It goes in here. So this is actually going to fit down into the Commodore 64 motherboard where we took the old crystal out of. Poor crystal. Alright, and now we're going to take some sharp wire cutters to our male pin headers, sounds painful, and chop off 4 pins out of a row of 6, just from the middle. You'll see why in a second. And the short end of the pins is going to push up into these pads, and cut out 4 from the top as well. And you only need 1 of these, by the way. That then gives you 2 pins which are going to go down into the Commodore 64 motherboard where the PAL NTSC switch jumper actually is. And then, if you don't have a motherboard assembly number ending in 425 or 466, you'll need a 3rd single pin. Alright chip tippers, we're getting closer, and now it's time to put our dip sockets into the board. Make sure the cutout of the socket matches the cutout illustration on the board. Push them in, and these are going to be for our PAL chip with the cutout at the top there, and our NTSC chip to match. Next up, this guy goes here. This is the switch cable header, and it will connect to our cable that connects to, you guessed it, our switch. Now your header will actually have 8 pins, so ignore the fact you only see 6 here. Just make sure there's a little space between the black plastic and the VIC-II² board. This will allow the switch cable to plug in. And make sure you insert it on the top of the card with the logo facing up. Next, it's time to install the crystals on the VIC-II². So we'll start with the PAL crystal, and it doesn't matter which way around you put these pins. And it's nice to just leave a little bit of space between the board and the crystal. Same thing with NTSC. And it should look a little like this. What's this, you may ask? Well, yeah, we decided that the VIC-II² should come packed with the Lumifix 64 on board. Now, if you've ever seen a Commodore 64 with this vertical banding, you may know that it's basically caused by unwanted interference coming from the clock signals on the VIC-II graphics chip. And the Lumifix 64 was created in 2011 by E5 Frog, and it basically cancels out those signals. Although it's never going to look as good as, say, emulation. But who wants that anyway? And this is the heart of the operation, the Texas Instruments 7414 inverter that cancels out or inverts those noisy signals. So we'll install that again, as always, making sure the notch on the chip matches the notch on the board diagram. And the next part of the Lumifix is these 47 picofarad capacitors. They're labelled 47PF on the board, and polarity doesn't matter, so you can put them in either way around. Now I should point out that all of this Lumifix stuff is completely optional, but you may as well do it as it's included in the kit. And then we've got these fancy blue trimmer resistors. These are the things you're actually going to turn with a small screwdriver to adjust your picture. Make sure you put them in so the screw end matches up with the little circle diagram on the board. And then last but by no means least, because they're literally doing all of the work on the board, it's our 4 relays. And the reason we've got 4 of these is because we're switching 8 things essentially. There's 4 pins of the VIC chips, plus 2 crystals, plus that jumper and a spare for testing. And each relay can switch 2 things, so 2 times 4 is 7. It's impossible to put these in the wrong way around, I think, although I probably shouldn't challenge you. Well, now give yourselves a pat on the back on my behalf because we finished the main board build. So just check over everything, make sure all the solder joints are nicely tented and none of them are making connections where they shouldn't. And then we'll clean up all the flux off the board with alcohol and that anti-static static brush. So let's build our cable. Now you can see that the plug has two sides. There's this rough side and a smooth side. So hold the smooth side facing up and locate the end of the cable that has the red wire at the bottom. And then you're just going to plug that into your VIC-II board. Again, ignore the fact I only have 6 pins here. Double check the red cable is in the position I've shown with the smooth side facing up, and then you can actually unplug it from the board if you want. Next, go to the other end and we're going to trim off the remaining wires because we don't need this plug here. Put that on Craigslist. Seems fine. And then just strip down each of these, exposing the actual wire. Then twist each of the wire ends. And then we'll tin the tips of the wires so they're ready to solder onto the actual switch. So this cute little guy is our mini grabber, and he's going to make it, or she, is going to make it super simple to hook onto the Commodore 64 power supply line. You'll find a couple of mini grabbers in your kit, and they connect to this wire and the one directly next to it. Now, don't follow this part of the video guide. What you're seeing me doing here is preparing the end of the mini grabber cable to connect to the 8-bit guy. To the 8-pin cable. Don't connect it to the 8-bit guy. However, you're not going to have to do this because we found a much simpler solution, which I'll show you in a second. But just in case you really love soldering or just want to learn a new technique, I'll show you what we do here. This is called a lineman splice, and what you do is hook both ends of the cable, connect the hooks, and then twist them together. You can then tin over that joint. Slide your heat shrink back onto it, and simmer for 20 seconds. This is the NASA standard for connecting wires, and means that both cables' hooks are actually pulling against each other with a solder joint around them, and in my experience sometimes the joint is actually stronger than the rest of the wire itself. So with that done to both mini grabbers, you can see they are effectively now connected to the VIC-II board. However, we just came up with an even easier way to do this. We found these mini grabbers that have the DuPont compatible plug on the end of the cable. So what you can do is carefully lift up the little black tab on the 8-pin cable and slide out the metal shield that's around the end of the wire. You can then do the same thing on the mini grabber, lift up that black tab, slide out its shield around the wire, and take the mini grabber's shield and insert it back into the original 8-pin plug. Saves a bit of soldering if that's what you want. Alright, well we are nearly there. The final major step is to wire up the switch itself. So what I'm going to do is again create hooks on the end of these tinned parts of the cables. And those hooks are going to make it super simple to hook into these loops on the bottom of the switch. And this switch of course is what we're going to use to flick between PAL and NTSC. And then just heat up the switch leg for a couple of seconds and add some solder. And it should look a little something like this. Keep going with the other cables. Now I'm not going to depict which colors go where because actually your cable colors might vary. So this diagram is intentionally grayscale. That means just follow the position of the cables, not the color. Simple, right? Pause video here. And when all is said and done, you should have a finished assembly that looks a little something like this. Well, now we can insert our card into the VIC socket very carefully. You can see how those crystal pins line up with the crystal area. So what we've got to do is create a socket for those. So go back to your female machine pins. Snap off 3 of them. And then you'll also want to snap off 3 separate individual pins. And those are going to go in this jumper section here. Again, depending on your board, you may only need 2. And when those inserted, place the whole assembly back down into the board and play around a bit until those pins actually go through the holes and poke through the bottom side of the Commodore 64 motherboard. Once you have them all in place and lined up, you can start soldering them. Once you've soldered all 5 or 6 machine pins into the C64, you can very carefully remove the VIC-II² and you should see the sockets neatly installed on the Commodore 64. You can then experiment with very carefully reinserting the VIC-II² into those sockets. Then pick up your cable and insert it back into that right-angled header on the VIC-II². Now grab your mini grabber, and we're going to connect both of these onto the inside of the power switch on the Commodore 64. Make sure you connect them the right way around as shown in the diagram. Again, follow the position of the cable, not necessarily the color. And I guess the final step is put our VIC chips back in. Again, make sure you orient the notch correctly with the notch on the dip socket. Make sure you steady the other side of the board when you push this down. And put the right chip in the right socket, of course. Now one of my chips has already got a heatsink on it, but in the kit we've thrown in some heatsinks and you should definitely put those on top of your VIC chips to stop them overheating. So now let's turn the power switch off and test our relays. Nothing. Oh wait, I forgot to plug it in. Okay, so now let's make sure the power's off and test our relays. And that satisfying click you hear is actually coming from the 4 relays, not from the switch. If we turn the power on, the relays fail to click, thus protecting your chips. So the only decision we are left to make is where to put the switch. Now we don't recommend drilling holes in these classic machines. You can run it out of the user port area here, but by some stroke of luck, this case actually originally came from a Ray Carlson repair where he'd also installed Jiffy DOS before this machine was kindly donated to me. So what the heck, I've got a hole there, I'm just going to stick something in it. So just take the nut and washers off the switch, stick the long thing through the hole, and screw the nut. What? May as well make a label. Oh, pretend you didn't see that. And you may have noticed I had to fit an extension to my cable to get the switch to the other side. You won't need to do that, but we'll just tidy up our work here anyway. Here's an alternative layout from beta tester Steve McGowen. Big thanks to him and all the testers, including Tim, Gaz, Stephane, and everyone else. And then it's time to put the top back on, not your jumper. And let's transport it to the studio for final testing. Ah, so satisfying. Now, earlier this week on my exclusive Patreon Lens, I showed this TV that I picked up whilst doing some thrifting for $4. I think you'll agree it looks pretty sharp. Yeah. So with the C64 off, let's flick into what I think should be NTSC mode and turn it on. Alright, we've got a pretty decent picture there considering it's only going through the composite cable, and I don't know really the quality of this TV. As you may have seen earlier, we can type input peak brackets 678, and that will return a 0 if the machine is NTSC. So that confirms NTSC is working. Now let's flick into PAL mode, turn the machine on. And yeah, I thought this might happen. So what this tells me is either my VIC-II² is faulty, or this Sharp TV, because I bought it in America, is NTSC only. In that case, PAL C64 won't work. You get a blank screen or a black and white picture. but what I can do is connect my FrameMeister XRGB Mini through to the HDMI of my big screen TV. If you've got a multi-region monitor, you won't need to do that. And yes, look at that beautiful PAL image. And we can just confirm that it is in PAL mode. For some reason on video it doesn't look as good as in real life, but here's a photo which is much more representative. And now the moment of truth, back to NTSC again. Now you can see the colour is a little bit worse here, and that's because, as we explained, NTSC is never the same colour. If you do see some of that vertical banding on your screen, which I've amplified here, remember you can use a small watch screwdriver in those Lumafix 64 trim pots and just adjust them until it fades away. Again, it's never going to be perfect like emulation, but we don't want that. And if you're upscale and you've got an upscaler, you can have some fun with the scanline generator. The image looks almost perfect like this. So with everything working, it's time to get the product to you. And for that, we upload the files to China, to a little company, I don't think you've heard of them, they're called PCBWay. Let's give you a little factory tour as they make the PCBs, as together we go through the keyhole. So after the PCBWay team member has checked the board and the traces and holes, a metal board is dry cleaned and cut, ready for use. And then it's off to the drilling room to drill holes and link the copper traces together. And the drill automatically selects the correct drill bit to use. Next is back into the cleaner. And this machine smooths the edges of the boards one side at a time. Now the middle layer of the PCB is non-conductive fiberglass. That means the hole has to be electroplated, so there's conductivity between the copper. And then, depending on the order specifications, more copper is added in this room. Dust-free, of course. Next, a layer of blue light sensitive film is added to the board. For that reason, all the lights in this room are yellow, so they don't affect the film. And it's the film itself that actually has the printed circuit board diagram on it. And then the board is sent through this UV printer, which hardens that film. This means only the circuit part is hardened, and the rest remains soft and can be cleaned off. And in this example board you can see how that blue material is the only thing left, and that's because it will actually resist the etching chemical in the next stage that etches away everything else. Next is into the AOI machine, or automatic optical inspection. If everything's okay, it's back to another yellow room, and this machine coats everything in epoxy solder mask. And then our retro recipe gets baked at 87 degrees. Then another sheet of film is placed on top, and this machine hardens that ink. When you peel it away, you can start to see the solder mask that's left behind. But in our PCB, we have a component legend that shows you what to put where. And these are printed on with an inkjet printer, albeit a little bigger than mine. Next, the board gets electrically tested to make sure all the traces are connected. And then it's time to cut all the individual PCBs out of those large production panels. And the team give the PCBs a final manual check over. And if everything looks okay, it's into the vacuum sealer. And a bit of bubble wrapping for good measure. Okay, so now our PCBs are in the packing room. And that means they're ready to ship to me and then to you. And you can order your VIC-II² sold completely not for profit now. Just check the links in the description below. Huge thanks to everyone that's helped with this one-year project, especially Sean Harrington. There's no way we could have done this without him. And thanks to you for watching and supporting this channel. So tell me, are you ready to take Vic to the future? I'll be back in a week or two, or maybe a week or two ago. Until then, subscribe below and cheerio.